this is very special. Thank you so much for having us tonight. And Miriam and Nick, thanks a lot for the lovely introduction. As Miriam said, this is our third attempt to come. And so for that reason, I need to thank Alice Lake-Hammond, who's done all the hard work in organising the roadshow, which is kicking off here tonight. So the roadshow is going to take us to 14 different communities around the South Island. And so you're the lucky first in line. And so we're very excited to spend the next couple of months visiting communities around the Southern Alps and, you know, around the whole island, because I hope by the end of this spiel of mine tonight, you should have a good idea about the potential for the Alpine Fault to affect all of us across the South Island, and in fact, right across New Zealand in terms of the indirect consequences of a major earthquake on the Alpine Fault. So, yes, thank you for having me. I'm Caroline Ochiston, and I work at the University of Otago, and it's been a real privilege for me to represent the science team involved in AF8 over the last 5 years. So we have about 30 Alpine Fault specialists who've fed the most up-to-date science into the program over the last 5 years. And so over the next sort of half an hour, maybe a little fraction over, I'm going to step you through what AF8's all about, the science that was pulled together in the early phases of AF8 to really inform what became then a planning process in terms of planning how we might respond to a future Alpine Fault earthquake in the coming years. And then I'll talk about what an Alpine Fault earthquake might be like in terms of the impact of ground shaking across the South Island and some of the other things that happen when earthquake shaking leads to other things such as landslides, and I'll talk through some of those what we call secondary hazards that are generated by big ground motions or shaking of the earth. So anyway, let's kick off. I should also introduce Julie at the back. You probably know Julie. She's going to be my clicker. In other words, she's going to change the slides for me as I progress through the talk. Normally, in a much more smaller and intimate venue, I can use a little clicker in my hand and do it myself. But because this is such a huge, wonderful theatre, I need a bit of help. So Julie, I'm going to mention or signal or something every time we're going to proceed to the next slide. So let's just kick off with the next slide now, please. And so the title of the slide tonight is what we can't predict when earthquakes are going to happen, but we certainly can do a lot as individuals, as communities, and as businesses, and as a country to get better prepared for them. So, what is AF8? Well, for those of you who haven't quite got the acronym yet, AF8 stands for Alpine Fault, and then the 8 part is the magnitude 8. And that tells us about the likely size of the next big earthquake on the fault, because the Alpine Fault has a sort of characteristic earthquake that it tends to produce over a period of time. And we'll talk more about that also as we go along. And so AF8 kicked off in 2016. It was all about bringing the science and the emergency managers into the same huddle, I guess, to figure out what this Alpine Fault earthquake might be like and how we can start getting better prepared for it from a civil defence perspective as well. And civil defence, I mean in the broadest possible sense, it's civil defence within our local councils, but it's also police and fire and all of the partner agencies that work alongside civil defence when the situation requires it. So, AF8 has tended to bring together a whole lot of agencies and people and scientists into the same frame. So we're calling it a sort of a multi-agency response which involves research, policy and practice across these domains that are typically off doing their own thing. We often hear about all this great science that happens in universities, but you know, this has really pulled it out in a way that we can really use it and then apply it to what we're doing in emergency management and government and all of those things as well. So hopefully it's quite useful. So where I normally start is just to explain a little bit about the situation in New Zealand and why we have high seismic risk. Why are there big earthquakes here? Why are there volcanoes and all of that stuff here as well? Because as we know, we've had a number of events over recent years which have caused us, you know, as a nation to really look at ourselves and wonder why we keep having these earthquakes and volcanic eruptions and things like that, like Whakaari a couple of years ago. So essentially, this is a world map, and you'll see here, I'm going to have to go all the way back, and apparently there's a gap here. I don't want to fall down the back of the stage. I'm okay. So here we have South America, North America going all the way around the Pacific Rim. This is the Pacific Plate, which is the biggest tectonic plate in the world. And around the margin of that plate is where all the action happens in terms of earthquakes, volcanoes. About 80% of the world's volcanoes are actually on the Pacific Rim. And as you can see, it cuts its way down through the South Pacific and actually goes right through New Zealand. So here on this side of the map, we have the plate boundary making its way right through New Zealand, off the east coast of the North Island, down across the South Island, and then off the coast down to the southwest. And so what that means, if we cut New Zealand like slice it up like a loaf of bread, and we look at it in 3 dimensions, you can see off the North Island, you've got the Pacific Plate diving down underneath the North Island, underneath the Australian plate. And what that does is, as it dives down, it starts to melt, and that's why we have our volcanoes that come up through the middle of the North Island. And then down to the southwest off Fiordland, we've got another subduction zone, as it's called, but this time the Australian plate is coming down and underneath the South Island. And so that's a very complicated tectonic environment, and that's why we have a very active landscape. We have lots of recently built mountains and volcanoes and things like that. And it's not just the plate boundary that needs to be of concern to us, because we have a number of active faults that are right across the country. So you can see that plate boundary in red, that's where most of our seismic hazard is. But of course there are a number of other faults right across and crisscrossing the country. Some of these will produce small earthquakes. It's obviously the plate boundary that is the biggest concern to us, because it's likely to produce big earthquakes. What about going back in time in terms of the earthquakes we've experienced as a nation over the last period since 1840? So these are the earthquakes greater than magnitude 7, and just the big ones. And so you can see, I think, about 20 in total, dotted across time. The biggest of those was in 1855, the Wairarapa earthquake. And that was a magnitude 8.2, the largest on record, the historic record. Then we had a cluster of events through the 1930s, and the biggest of those was the Napier event in 1931, which still remains our deadliest earthquake on record. So about 258 people were killed during that earthquake, mainly because the town had largely masonry construction, and so a lot of collapsed and killed people in that way. But also there was a fire that followed that earthquake because of the gas reticulation in the town. So the fire also caused a number of deaths. And then a number of years went by. We had the Inanga-Hua earthquake in 1968, and then a period of about 40 years without any major earthquakes. And I would argue that this is a time when New Zealand got a bit complacent about earthquakes. We didn't really, they'd sort of gone beyond living memory for a number of people, so there's a big gap in the record here. And then some of you might not have heard of Resolution Island. Does anyone know where that is?
Dusky Sound.
That's right, down in or is it Dusky? No, it's Doubtful Sound, isn't it? Anyway, it's down in Fiordland. And that was a big 7.8 earthquake in 2009, but it didn't really do a lot of damage to people or property, because it was in a very, very remote part of the island. And then, of course, 2010, none of us will forget the beginning of the Canterbury earthquake sequence, which, of course, you'll notice that the February earthquake doesn't feature on this chart because it was a magnitude 6.3. And then the Kaikoura earthquake. So we seem to be having another, what appears to be a cluster of higher seismicity happening right now. So that's the sort of history of earthquakes through time in New Zealand. And this is an image, hopefully you can see it all right in the back. This is actually a satellite image of the South Island, just the central South Island. So Waimate's just down here, I suppose, probably just off the map. And there's Banks Peninsula. And I've got a couple of red arrows there which show how the plate boundary is moving. So you might make out quite a straight line up the west coast. That's the Alpine Fault there. And the Australian plate on the western side is moving relatively up on the slide. And then the Pacific plate's coming down and pushing, sort of slightly kind of squeezing together the South Island, coming in at about the rate that your fingernails grow every year, about 30-something millimetres per year. Now, we'd be okay if that movement was just gradually coming in slowly but surely. Unfortunately, with this plate boundary, that energy coming in is kind of getting stored up. It's stored up like in a spring, and eventually it'll break in an earthquake. And so now we have this energy storing up, and at some point in the future there'll be quite a big shift across that plate boundary in a large earthquake. So this is, again, the Southern Alps, and we'll click through the Alpine Fault will show on here now, Julie, thank you. So this is a very big, long fault. It's about 500 kilometres long from coming onshore at Milford Sound all the way up to around Springs Junction, where it branches off into the Marlborough Fault system. And down south, of course, it continues offshore into the subduction zone off there called the Pusica Trench. And we've known about the Alpine Fault since this very intrepid scientist, Harold Wellman, was at work on the west coast in the 1940s, doing a lot of mapping and exploration over there. He was actually looking for gold and other minerals too. But as he was mapping the geology on the coast, he started to observe some features in the landscape, the different rock types, and it told him that there was something quite major happening on the coast. And he actually proposed this Alpine Fault. He named it the Alpine Fault back in the late 40s. The geology fraternity out there just didn't really believe him, because no one could imagine there being such a long fault anywhere on the planet at that stage, because this is very early days of the way we used to do science and on plate tectonics and all that sort of thing. So as we move into the geology of the South Island, you can see this stripe of blue rock here, and it comes out again up in northwest Nelson. Harold Wellman identified this rock as being quite distinctive. It was called it's actually called the Dun Mountain Ophiolite Belt, which is quite a funny name. We call it the Red Hills because it's actually a red-coloured rock. And it's the nature of the rock means that nothing really grows on it. And so I think the next slide might show us, perhaps the slide after that he made the connection that these two pieces of rock had at one point been across the fault from each other, and they'd been moved apart by earthquake activity on this fault over millions of years. So they were now 800 kilometres away from each other. And if you show the next slide, Julie, I think we'll see the Red Hills. So you can see this very distinctive, this is up in northwest Nelson, the Red Hills there, and down in Fiordland, you can see it poking out there. The same rock just moved apart over millions of years. Quite amazing stuff. And Harold Wellman was the guy that made that connection. So, great story. And of course, the Alpine Fault is part of the reason why we have such a beautiful landscape in New Zealand and in the South Island, because the movement on the fault is squashing together the Southern Alps and pushing them up at about 10 millimetres per year. And so these are very young mountains. They've been pulled up over just a short, maybe 5 million years, which in geological terms is quite a short time. And because the mountains are there, and because we have the weather systems coming along from the west, they drop their load of rain west of the Alps, and that's why we have our beautiful temperate rainforest. And that's why we have a beautiful, dry, hot summer east of the Alps in Canterbury. So just, we have a lot to thank the Alpine Fault for when we think about it in that way. So how do we know about the way the Alpine Fault has behaved in the past? So up until about 2011 or 12, we knew about 3 earthquakes on the Alpine Fault back in time. The most recent one of those was in 1717 AD. So if I was really tall, I could point up to the top of that slide, and you can see 3 little blips going down on an angle like that. And this is time going back from present day all the way back 8,000 years. So that's the record that you're seeing across the top. So we had 3 earthquakes on the record from around the lower part of the fault near Haas. That was where the evidence came from. But in 2011 or 12, can't remember which, a team of geologists from GNS Science went a bit further south on the fault, and what they found in a couple of creeks down there just blew our minds in terms of what the Alpine Fault had done in the past. If you click to the next slide, Julie, we'll see now we know of this number of earthquakes from 2 sites down in South Westland. And so this evidence is telling us, and I think if you click to the next slide, Julie, you'll see this is where the data came from. In this box here, it's showing the sediments in this image, and you can see stripes in the riverbed. They took samples of wood and other things from inside those sediments, which told them the date. And each one of these stripes represents a seismic event on the Alpine Fault. during which you get a whole pulse of sediment that comes out of the mountains and it accumulates down in the creek. And this is what we're seeing here. So that's a really phenomenal record of earthquakes going back in time. And Julie, if you click to the next slide, what we're seeing here is 27 earthquakes over a period of 8,000 years. And what this also tells us is that there's a very long record of the earthquakes sort of popping off at pretty regular intervals through time. They're not exact, of course, this is nature, but they are happening almost like a sort of every 300 years another one pops off. And so what that tells us is we have a regular cycle of energy accumulating or stress accumulating on the fault, and then an earthquake releases it. And then it builds up again, and then it releases it again. So that's a really incredible world-leading record of a long record of earthquakes on a fault, better than any record anywhere in the world. This is happening roughly every 300 years. The last one was in 1717 AD, and so there's a real inevitability about the next earthquake happening, probably within the lifetimes of many of us in New Zealand today. Yeah. So what's this Alpine Fault earthquake going to be like? Okay, so what we did back in 2016 was we got a team of seismologists and geologists and engineers into a room for 2 days, and we nutted out what the scenario of this earthquake might look like. So a scenario is just a way for us to sort of focus our energy. It's an example of what might happen during a large earthquake in terms of the ground shaking and the intensity of shaking. But it doesn't tell us everything, of course, because this is just one possible way the Alpine Fault might behave. It could happen in any number of ways, so we have to keep that in mind when we talk about scenarios. But we had 3 to choose from during our discussions. The first one is the small one in the top right of the screen. We called it the north to south rupture. That's because the red star shows where the earthquake begins and how the energy then moves out from that point. Now, of course, with a big, long fault like this, it's quite important to know where the earthquake starts. I've got a feeling I'm going to have to take a drink of water. Sorry, I'll carry on. So it starts in this scenario up in the northern part of the fault, and then the seismic energy rolls out from there. In the next one down, we have a central epicenter, and then the energy radiates out in 2 directions. And in the main one here, called the south to north, that's where the earthquake begins in Milford Sound, and it pushes its energy up towards the northeast. Now, we chose this bigger one as our scenario earthquake because not only is it scientifically credible, it's also the thing that will test us the most in terms of impact on our communities, on our infrastructure, excuse me, and everything else. So we decided to go with the south to north rupture. So just bearing in mind, we could have chosen any number of different scenarios, but this one we selected for a number of quite important reasons. So this is a blow-up of the north to south one, and you can see the colour scheme. It's not great. I'm sorry for those in the back, it would be hard to see this. But what we're seeing here is intensity on the scale, so that's the modified Mercalli scale. A magnitude of 10 or 9, this is an intensity of 10 or 9 or down to 4. And the intensity is the amount of damage that ground shaking does to our built environment. Excuse me. And so you can see in this scenario for the north to south, we have colours down in the bottom of the South Island, which are mainly yellow or green. So those are the lighter, the less intense areas of shaking. And then as we move into the west coast, you can see darker oranges and reds. That's where the most damage will be experienced. Then we have the central one here, as I mentioned, and we'll click through to the final one, the south to north, because that again shows that the lower South Island in this scenario is experiencing less damaging shaking, thank you. And as we go into the northern part of the South Island, we're getting into sort of 7s, up into 8s and into the 9s and 10s, which is the most damaging part of the ground shaking. Thank you. I'm going to have a wee break in a minute because we're going to have a video. So, Julie, I think the next slide is the video. Is that right? Yeah. So Julie's going to flick us over to the internet now, and we can watch this animation of what that might look like, because it helps, I think, to imagine this as it happens over time. So on this animation, you'll see the epicentre down in Milford Sound. And then we watch as the time ticks across. You can see the time ticking away at the top left, top right of the screen. You can start to see the intensity peak starting to emerge here. Now this is all relative, of course, that doesn't mean vertical motion. This is just the intensity of ground shaking. And you can see the seismic waves starting to move up the west coast and also out across the South Island as well. So we've got a minute since the earthquake started. And you can see those peaks in intensity as it starts to move up the west coast. So we're starting to get into the oranges and reds. In a moment you'll see the peaks starting to emerge as it's building up the west coast. Now, as these seismic waves are hitting the Canterbury Basin, you probably know about this effect where the sediments that are sitting underneath us here, they're quite deep sediments from the rivers that have crossed across the plains over time. What tends to happen is the shaking bounces and reverberates around those sediments, and it lasts a bit longer in that space. So you can see right through Canterbury, there's still got lingering seismic waves coming through there. So after 3 minutes, this earthquake is still making its way up to the northern part of the South Island, and it will carry on across Cook Strait and start to be felt in the North Island as well. So that's quite a sobering thing to watch, and for some of you that might be quite cause a bit of anxiety, but this is what happens on big, long faults. It doesn't just all roll out within 20 seconds. It takes time for those seismic waves to move across a large area. Wow. Any questions about that while we have a wee pause?
You just about have a tsunami in Wellington Harbour, wouldn't you?
Well, no, in this scenario, we don't have a tsunami being generated on the seafloor because all of this earthquake's happening on land. So we're not seeing a displacement of the seafloor in this particular scenario. But what we could see is in some of the lakes across the South Island, if they happen to be around high mountains and some rock falls into the lake, then it's possible to get what we call a rockfall tsunami. So that's a lake tsunami. And you get rocks plunging into the lake and causing a wave to travel out across the lake surface. And so the key message there is that if you feel long, strong shaking and you happen to be around a lake near the Alps, then you'd move away from the margin of the lake. There's also another phenomenon called a seiche, which is where, imagine you're lying in the bath and you move your legs up and down a bit and you start to get a sloshing effect around the edge of the bath. It's a bit like that in a lake, which is a body of water that's shaken during an earthquake, and that starts the wave oscillation across the lake surface, and you can get a bit of sloshing around the margin of the lake as well. So a couple of things to look out for if you happen to be around a lake during a significant shake.
Your simulation showed if it started at Milford, what happens if it starts up north? Is there any difference? Or is it all...
Well, yeah, as I say, yes, it does make a difference because the direction that seismic waves move in will affect the island in different ways. So you're quite right, there will be differences. The animation that we have for the south to north rupture that you've just seen is the only one we have at the moment because my colleague Brendan Bradley up at Canterbury, who produced it, it requires a huge amount of computing power. It's a really big program that you have to run to make that happen. So he's only made the south to north rupture into an animation so far. But yeah, we should ask him to do the other ones as well. So,
what happens to all the dams that we have in the area here?
yeah, that's a really good question.
Dams, etc. Are they going to hold out or are they going to break?
Yeah, the dams, that's a really good question. We often get asked that. And we did a presentation in Twizel a couple of years ago, and we had a dam engineer in the audience. And I was really pleased because I'm not an expert on dam engineering. I'm not an engineer at all, actually. And so he was able to step in, and I observed his response to the crowd, and it was good for me to know as well that these dam structures are engineered to a particularly high standard, international standard. And they're really quite comfortable in the fact that their dams are built to withstand significant earthquake shaking. And so they're, I felt quite confident about that. Of course, there are things that can happen to dams. They are built such that if there is a significant shake, they will go into automatic lockdown, shutdown rather. So to protect their processes, they shut down and they require electricity to restart. So it's called a black start. They need electricity to get back up and running again. And when I get onto the section around the distribution of electricity, if there is disruption and there is a blackout in terms of power not being available, that can make it difficult to get the dams back up and running again. But yeah, great question. Was there anything else anyone wanted to ask at this point?
Yeah, the person over here, down here on the
Yep.
right.
Yeah, I think the question is answered, but I was just asking myself if the dam is really cracking, even if it's high standard or something like that, you never can adjust a big earthquake with high standards. It's just not possible. What will happen? Will Glenavy be on the water?
Look, I don't know enough specific detail around the situation here, and I know the Waitaki Valley is one of the critical areas for our hydro network, and Lake Dunstan is one of the most important assets in terms of the network of dams across the Waitaki district. But I don't know enough about that to give you a really clear answer, I'm afraid. Yeah.
The dam owners have, be it Meridian or Genesis or something like that, they do have flood plans for this whole valley,
Yeah.
for Waitaki Valley. Glenavy is definitely it's pretty much a matter of how long it takes for that wave to get, if the Waitaki breaks,
Yeah.
for example.
But remember that we're quite a distance from the Alpine Fault here in the Waitaki Valley, so we're not quite 200 kilometres away from the Alpine Fault. And by the time the seismic shaking gets across to here, I know it looked quite significant in animation, but by the time it makes its way across here, it's not the really high intensity shaking that you would experience right on the Alpine Fault. It would tend to be more of a sort of a rolling motion rather than a very agitated up and down motion. And so for those of you who maybe felt the Kaikoura earthquake, the distance that it's travelled, it starts to become a lot less intense as it moves away from the epicentre over a couple of 100 kilometres distance.
It wasn't clear in the modelling what the depth of the earthquake, you spoke about magnitude.
Yeah.
You didn't tell us about the depth at which the primary event occurs. Is that down at the subduction zone?
Yeah, really good question. Obviously that's a really critical factor in determining how damaging this earthquake's going to be. Because if you have a magnitude 8 earthquake at 150 kilometres depth, it'll do a lot less damage than if it's at 10 kilometres depth. So with the Alpine Fault, the seismologists would expect it to happen somewhere between 10 and 15 kilometres below the surface, because that's what they call the seismogenic zone right underneath the Alpine Fault, and so it will be around that sort of a depth. Yeah. Shall we move on to this next slide, which is really trying to zero in a bit more on the Canterbury district for you, because I know that this is relevant here. And so we've got the outline of Canterbury on there, and hopefully you'll be able to make out that the colour scheme takes you from, and it's even hard for me to tell because it's all, so we've got MM4 at the top of the slide now, that's the less intense, and then going down into the oranges down here, somewhere between intensity 5 and 6 and 7, but you're down here just across the border into Canterbury, so you're in the sort of lighter green, yellow kind of zone. Is that right? Is that where you are on the map? I didn't check this. I normally put a dot where we're talking to the community. Is that right? You're in that lower part of the Canterbury there. So that sort of damage, that sort of intensity will be felt. There could be some minor damage to some of your vulnerable buildings. So heritage buildings might experience some minor damage. We'll certainly feel it, and we might be woken up by this kind of shaking in and around this community. But I think one of the important things to remember is it's not just about the direct impact or the direct consequences for your town, because with an earthquake like this, it will have indirect consequences across the South Island. And when I'm talking about indirect consequences, I mean things like road access, distribution of electricity, the ability to buy a loaf of bread, for example. There'll be some disruption to the flow of goods and people around the South Island for a period of time. And so even that you might have fairly mild consequences here in terms of those direct impacts, you can expect to have indirect impacts from things that I've just mentioned in terms of moving around and the delivery of goods, and potentially even power outages for a period of time after this event. So earthquake hazards, I'll talk a little bit about these now in terms of what begins as a ground motion. Sorry, Julie, can you flick to the next slide? We'll flick on to the next part here too. So often when we think about earthquakes happening, we're quite concerned in the moment with the ground motion that we'll experience, and it might go on for a couple of minutes, and then it stops and you take a breath and assess what's happening around you. But in terms of the secondary hazards that are driven by earthquakes, we have to think a bit longer term into the days and weeks and months and even years that follow major earthquakes. And so, for example, here's an example of a secondary hazard cascade, as we call it. So an earthquake can lead to a landslide, for example, in the high Alps. When mountains shake, they tend to drop a lot of material down through the, out of the hills and into the valleys, and that's, often landslides or debris flows and things like that. Now, these landslides might cross a river valley. Here, for example, you've got a landslide coming down and damming up a river, and this will be quite common on the west coast, where we have a lot of, active river systems with steep sides. And then sometimes those dams become unstable quite quickly. Within a day or two, they might start to overtop, and sometimes that overtopping can be quite significant, what we call a dam break flood, and that's obviously high risk for anyone who happens to be downstream or in the communities or townships below these rivers. And so the key message here would be, understanding your rivers in and around your community. If you see your river change in terms of the amount of flow, or it gets cloudy and dirty, it might mean that something's happened higher up the valley that you need to be worried about. And so these sorts of secondary hazards can really play out over a period of time, and there are others that, of course, we're all familiar with aftershocks. That's a secondary effect of a big earthquake. We always have these series of aftershocks that happen afterwards. Weather events can also come along and make matters worse, in terms of how we respond to earthquakes. If you're trying to launch a response and there's a significant weather event, evacuating people out of the west coast will be made a lot more challenging. And then, of course, fire, I mentioned, as a consequence of the Napier earthquake, made, again, the response a whole lot more challenging. And so these sorts of secondary hazards are part of what we've been considering for the AF8 scenario. And sometimes they can be worse than the initial ground shaking. So think, for example, the tsunami that followed the Boxing Day earthquake, the big earthquake that happened and produced the tsunami, which went on to kill about 300,000 people around the Pacific and the Indian Ocean. Japan, obviously the tsunami was the secondary hazard that caused a lot of damage and death. And in Christchurch, it was the liquefaction and the rockfall around the Port Hills that we probably remember as these two types of secondary hazards that had a really significant impact. In Kaikoura, it was the landslides, and you can see here Oho Point, we were just covered in a massive landslide which took more than a year to repair. And so these secondary hazards are something we have to keep in mind. It's not just about the earthquake and the initial feelings that we have and the impacts that has, it's what can follow later. And in alpine regions like the Southern Alps, these are particularly something that we need to be thinking about. And so here, for example, we have the state highway network, the roads around the South Island, and the kind of ground shaking caused by the earthquake that those roads might experience. And so as we move into the red and orange colour again, that's where the roads are going to experience the worst shaking. And you can see here, of course, the West Coast State Highway 6, through all of the Alpine passes, the Lewis Pass, Haas Pass, Arthur's Pass and Milford Road, all experiencing quite damaging shaking. On this model here, we've got a model actually produced by my colleague down in the audience, Tom Robinson, for his PhD, which was a landslide model based on a magnitude 8 earthquake. And again, these warmer colours as you move into the Alps showing the highest likelihood of landslides occurring. So obviously in the higher Alps, that's where we expect the most landslides. And then if you take this model and you overlay it with the highway network, we can see again the issues that we're likely to experience with landslide damaging the road. So again, through Arthur's Pass, particularly down sections of State Highway 6 down the west coast, Haas Pass and going into the Milford Road landslide, coming across the highway and causing damage and destruction there. So these passes, very unlikely to be able to go through there for a period of time after the Alpine Fault earthquake, and we've heard various estimates of up to and well beyond a year of road closure on some of these passes. Again, so this is, sorry, we have clicked to the next slide. This again is the same landslide model, but when we overlay this time the electricity network, Julie? There, the electricity distribution network, you can see that the real pinch point here is Arthur's Pass, because there'll be significant landslide across the pylons and poles, etc., going through Arthur's Pass, and these are going to be a real headache to fix, because of course, for those of you who know, Arthur's Pass is just scree slopes all the way down through that valley, and accessing those places when you've got aftershocks reverberating around those valleys is going to be very challenging, and it won't be possible necessarily to fix those pylons for a period of time. So that means that there are some vulnerabilities in the network of power distribution across the South Island. And of course people and telecommunications, because our telecommunication networks often rely on electricity to work. And so if the power goes down, then we may not be able to get on our cell phones and jump on social media to find out what's happening necessarily. So we might have to use different forms of communication in the first few days or weeks for some areas after a big earthquake. And of course the people aspects of this are hugely important. Around the Southern Alps we have a large number of small communities who are often remote. They're accessed by State Highway 6 down the west coast, and between the bridges and the roads being damaged, these communities might experience quite a lot of isolation in the weeks and months that would follow an event like this. And we saw this after the Kaikoura earthquake. This is the Puppeteer fault coming across the highway and the rail network and going out and forming a brand new reef right off the coast. You can see that surf break there. That's all thanks to the uplift on the Puppeteer fault, which was one of the faults that was involved in the Kaikoura earthquake sequence. And so what we learned from the Kaikoura earthquake was, community isolation and a very long period of time to reinstate the highway had a huge number of direct and indirect consequences for not just the Kaikoura district, but also other communities right around the upper South Island, because some of them actually experienced a lot of extra pressure from more people coming, and that actually caused almost as many headaches as not having anyone able to come at all. So there were certainly a lot of impacts that we couldn't have predicted from that Kaikoura earthquake. Another one, I showed you this image before of Oho Point with all the landslides, and then the next image is what happened here over the next 13 months as they repaired that huge landslide. A technological feat of brilliance when, in terms of what the engineers were able to do here. And the uplifted coast gave them a bit more space to create the highway, bring it up a bit, and also develop some new sort of tourist pullover areas just a bit further up the coast. So it's made it, it's really improved the driver experience up this coast, but it took a huge amount of money and time to do that, of course. And then the other image showing the one of the faults, the Kekarengu fault this time, uplifting one side of this house. So this house actually just happened to be sitting right across the active fault, and it moved 10 metres horizontally. You can't really see that from this image, but one side moved 10 metres up, maybe a couple of metres here, and this is of the order that we would expect for an Alpine Fault earthquake. When it moves, we're likely to get that sort of 10 to 12 metre of horizontal shift, and a bit of an uplift of maybe 2 or 3 metres as well. So it's a similar kind of thing to what we're seeing here, but the good news is that house actually remained fairly intact. What damaged it the most was probably the chimney falling over, but the guy that lived in this house stepped out of his house during the event, and kind of his foot, it was moving as he tried to get out of his house. So it was quite an amazing experience for him, I guess. But just click through here, Julie, we can see there were 21 faults involved in the Kaikoura earthquake, which ruptured, in other words, broke the surface like this. This is a surface rupture, for 180 kilometres across the Kaikoura district in North Canterbury. In an Alpine Fault rupture, we'd expect about 400 kilometres of this kind of surface rupture to happen up the west coast. So key messages here, and I'm winding up now. So this is some really key messages about the Alpine Fault, and you can read through those, but essentially what we have here is a very high probability of a magnitude 8 earthquake or thereabouts on the Alpine Fault within the lifetimes of many New Zealanders today. This is just one particular scenario that we presented today, but it won't be exactly like what we've talked about. It'll be something different because they're never exactly as you'd expect them to happen. There'll be direct and indirect consequences across the South Island and into the lower North Island as well. This, as I showed on the animation, we'd expect that ground shaking to carry on across Cook Strait and have some impact on the lower North Island as well. The widespread nature of those secondary hazards are going to present not just immediate issues for us, but also into the longer term as we see a lot of that material and the landslides coming down through the river systems over a number of years and causing some headaches for people and farmers, etc. on the west coast. There could be periods of isolation for some of our communities, and we have to accept that that's probably going to happen, and we need to get our communities better prepared in a number of different ways to deal with that. Communications will be challenging. We need to remember that we can't predict exactly when earthquakes will happen, but we can get ourselves better prepared. And, you know, communities like yours are really well placed to do as much preparation in advance as we can to make a difference to our comfort after this event. So next slide, Julie, is just a few ideas for how to prepare. And this is where I'll be calling on Nick to come into the conversation for the question time, because I know you'll have a lot of questions about the things you can do for yourself, for your family, for your community to get better prepared. And so here are just a few ideas, and it really starts with having conversations. You know, most of you will know your neighbours and you'll understand maybe the specific challenges they might have or the specific ways that you could help them or you can help each other. So that's a really good place to start. Making an emergency plan for your family, just again having conversations with the kids and saying, hey, if this earthquake happens and we might be on the other side of town, this is where we're going to meet, this is what we'll do, we've got some stuff prepared at home that will help us to get through this together. Make an emergency kit and remember to refresh it when you can, if you're able to do that. Making sure you've got enough medication. I know that that's, for some people you have to be prepared to have medication that you might need, or for the needs of your animals, for example, looking after your pets as well. That's a really big thing for some people. Having a getaway or a go bag, a go bag of, look, if you're asked to evacuate for, let's say it's a flood event, you had a flood earlier in the year, didn't you? Let's say you were asked to evacuate, what would you take with you if you needed to get out of the house quickly? Now that go bag might be useful in an earthquake as well, so by getting prepared for an earthquake, you're also getting prepared for a number of other particular events that might happen. So anyway, good places to start in terms of places to find out more about this stuff. The Earthquake Commission are really useful. In fact, we've got a couple of our colleagues from the Earthquake Commission here tonight, so if you had any questions that they might be able to answer, I'm sure they'd be willing to help with that. And of course, neighbourhood support and National Emergency Management Agency and all of the civil defence groups can help you with their local community response plans as well. So I'll stop there, and hopefully on the next slide I think it's just a thank you and do you have any questions part of this, and I'll invite Nick up onto the stage with the mic as well. Perhaps he can hand that round if anyone has a specific question.